Hello, everybody. I will. Did you work in your models? I will stop sharing this one, and we will start new slides. I mean, today we will finish early. So now we will. So today we will talk about some data pre-processing, but also we will revise some tasks we need to revise in the example for data pre-processing. I mean, we have been working in those inseparable data sets. So it's just the definition for, inseparable data sets. I mean, if you want to get a definition, inseparable data sets, it's the property of two sets of points. Those two sets are linearly separable if there exists at least one line in the plane with all points of the first set on one side, and of the line and all points of the other set on the other side. So this is the definition of separable. This idea also can be generalized to higher dimensional Euclidean spaces if the line is replaced by hyperplane. So this one, for example, we can have a line here, correct? So this group will be one line, and this group will be another line. So in this case, it's linearly separable. So if we have two types or two classes,
you're not sharing your.
You cannot see my screen?
No.
Okay. We will. It's a screen number one. It should be okay. I don't know. Can you see it now?
Yes.
But I don't know which. Yes. Can you see it now?
Yeah, seeing the slides. Yeah.
Okay. Okay. So this data set, I'm talking about this one first, and this data set, in fact, it's separable because we can find a line, and this line can be used for, separating it into two different groups. We can extend it to multi.
You're only sharing the PowerPoint, though. You're not
yes,
sharing
PowerPoint.
anything else. It's only
yes, only the PowerPoint. Yeah. Can you see my PowerPoint with my annotation?
No annotation, no.
Okay. So. Maybe I can just close. You cannot see my PowerPoint? Okay, close all PowerPoints.
See the PowerPoint, but just not the annotations. You're not seemingly not drawing.
Okay, so I will enlarge it and.
If you go full screen instead of being like this, then it used to work. Yeah.
Yeah. So no, it works.
Try drawing and we'll see.
Okay. Is it fine now? So this one. Is it working?
Yeah.
That's very good. Very good. So this inseparable data set, we can, if we can draw a line between any two classes, a straight line in this case, and one set will be on one side of the line and the other set will be on the other side. In this case, this is a definition of separable. We can extend it to multidimensional space also. So if we have x1 and x2, right, and x3, for example, so we can, this one, in this case, the line will be a plane, but otherwise it will be inseparable. So exclusive OR is a very good example, in fact, of this inseparable data set. And the exclusive OR, in fact, it's, exclusive OR, it's binary operation, which is used in cryptography. It's very important in computer science. And this is the truth table of it. So if we have two inputs, so X, it's 0011, Y, it's 0101, it will be 1 when when x not equal to 1. So it will be like this one. And then when we are plotting it, we will have two classes, the blue class, which is 1, and the red class, which is 0, for example. So this one will be 1, and this one will be 0. So if we can look into this data set, it's impossible, in fact, to find one straight line which can divide it into two sets. So you can just imagine if we selected a line like this one, what will be the accuracy? In this case, in fact, maybe if this one is correctly classified, so this one will be incorrectly classified, so the accuracy will be 75%. So it's impossible to find a straight line which will divide it into two separate lines with accuracy of 100%. But this kind of data sets, in fact, we need two lines. So this one, it's a 0, this one, it's a 0, this one 0, this one, it's 1, and this one, it's 1. So as you can see it here, we have two lines. So in this case, all data points between the two lines will be 1, and all data points above the line and below it, it will be 0. So in this case, we can classify it. How can we get those two decision lines? We can get it by two perceptron. Each perceptron will generate one line, right? So for this simple data set, we cannot use a perceptron, but we need to use at least 2. So we will use 2, right? We have here 2 inputs, so it's x1 and x2. So it's connected like this one. And we need finally one here to make, collecting decision. And finally, the output here, y, it will be 0 or 1. So this is the minimum, in fact. This is the minimum one which can be used for classifying this problem, because it's inseparable. This one will generate one line, this one will get one line, this one will get another line, and this one will make ending and between the two decisions. So finally, we can have a single decision. So this kind of problem, it's impossible to solve it using one decision line, but at least two lines. We can have 2 lines. And how can we generate those 2 lines? We need 3 perceptrons. And when it's 3 perceptrons, it's multi-layer perceptron, correct? Now it's not a perceptron anymore, but it's a multi-layer perceptron. So it's a neural network. So iris, for example, we were able to classify iris using a perceptron, but we cannot do the same here using XOR, because XOR, it's inseparable. This is the confusion matrix. And then when you see it in the confusion matrix, its accuracy, it's 100%. So all 0 cases, we have here 2 cases, 2 0 classified as 0, and the 2 1s classified as 1, right? So this one, so the accuracy here, in fact, it's 100%. So how can we do this? I got this example from one of you, in fact, last week. So I just defined x and y, and I used the multi-layer perceptron, multi-MLB classifier from sklearn, and I used one hidden layer, and the hidden layer has 2 units, correct? So when we draw this one, it will be the same. In the hidden layer, we will have 2 units. In the output layer, of course, we will have only 1, because this one, it will be decided by the data set. We have here 1 decision. So this one will be decided by this one. And the number of inputs will be decided by the data set. So we'll have here 2 inputs. So it will be like this one, x1 and x2. Each one of those will create a line, and this one will just make the decision. So this one will be 0 and 1, for example. And we have this one, it will be omega 1, 1, omega 1, 2, omega 2, 1, and omega 2, 2. And we have the bias values here, B1 and B2. We will have also here V1 and V2, for example, and we have here B3. So this is the MLB classifier. So XOR problem, it's very simple, but we cannot solve it using a perceptron. We can, in fact, solve it if we will use again feature construction similar to the circles. But this problem, we will use the data set as it is. So in this case, we need to have more complex model. And this model, it will have 2 times 2 weights, 2 times weight 2 plus 2, correct? Those are the weights of the first hidden layer, plus the output layer, it will be 1 times 2 plus 1. So total number of parameters here, it will be 2 times 2, it's 4, plus 2, it's 10. So it's 13 weights, right, to solve this simple problem. So number of parameters will increase exponentially, in fact, with increasing the complexity of the dataset. In this approach, we build the model, we trained the model using x and y. We used it for predicting, for all values of x. We have just only 4 data points, so I didn't divide it into training and testing. I just used it for training the model. We can print the coefficient of the model, right? we have the coefficient. I mean, last time we have, I guess, coefficient and intercept when it's a perceptron.
Question.
Yeah.
Did you do that wrong a bit? I'm getting 9, not 13 total parameter.
2 times 2, it's 4. Yes, 6. Yeah, you're correct. Correct. Yes. So you are correct. It's 9. Yes. After that, we will plot the decision line. I mean, in plotting the decision line, I prefer to go for this grid. So we will generate values for x1. If we make it like this one, I have here x1 and x2. So I can generate values for x1 from 0 to 1, and for x2 also from 0 to 1. So I will create a grid here, and I will just apply the model. We have this model. It's called the model. So I will apply this model at each point to plot the decision line or decision boundary. So I will just do it like this. So I generated values for x1 and x2, they are the same, right? We generated this grid, and I used the model to predict the decision for each point in the grid, and I plot a contour plot for it. And also we can get the confusion matrix for y and y predict. So so finally we can get those nice decision lines from this. I mean, this is the results, in fact, from this code. We can get those decision line, and in this case, all points which are located between those two lines will be classified as 1, and all points above and below it, it will be classified as 0. In the next example, in fact, I will just generate a data like XOR. So this one, it's also like XOR. Do you see here XOR? So it's 1, 0. So I will just generate it, but using random numbers. So if I divided this one into 4 sections, you can say that this one it's a +1, this one it's a +1, this one it's a 0, this one it's a 0. Correct? So I'm just generating a data look like XOR because I want to classify it. We need also to find a line, but this one there are some, I mean, overlap between. I mean, it's impossible. If I want to draw a line here, it will be more complex. So I cannot use a straight line here. Maybe I need something more complex, right? So maybe I need to find something like this one, curvy like this one. Now it's more difficult, right? So now we need to find something more complex. So we need to make our model more complex, right? So I will generate those data points using this part here. I'm just generating each class consists of 100 points. And this is offset of classes or just the distance if I need to have a gap between the classes, and I'm generating it. And after that, I will use the MLB classifier also from sklearn. So I will use also MLB classifier, but in this case, I will make it more complex. So it's still two hidden layers, but the two layers, but the hidden layer, in fact, it has 20 units. You see, if you selected two, you will get a model, of course, but the accuracy will be really very bad because you will have two straight lines. So maybe the accuracy will be 50%, 60%, something. So I just increased the number of units in the hidden layer to make it more complex. So it's the same. We will have two inputs, right? Because we have x1 and x2. So it will be like this one. We have x1 and x2. This layer, it will have 20 units. And in the output, we will have only one output. So it will be like this one.
Question, Ibrahim.
Yes.
How do you know how many hidden layers you should choose?
In fact, there is no rule for it. It's a trial and error, or you can use the search grid, for example, to select between numbers. So, but if you want, I mean, good advice, you can start from some number, right? You can start by 5, for example, or 10. If it is one hidden layer, and you can see that, I mean, the accuracy, is it good or bad? If it's very good, you can go a little bit down, so you can decrease it to avoid overfitting. And if it's not good enough, you can just increase it step by step. So it's like trial and error, in fact, because there is no rule for it, in fact. So I can select the two hidden layers. So I can start with one hidden layer and the 10 units, for example. And if the accuracy is not good, I can increase number of hidden units, 20, 30, 40, 50. If the accuracy is still not good, I can add one more hidden layer, right? And in this case, I can start from a base model and try to make it more complex to improve the accuracy. But I mean, this is the only way, because there is no rule for selecting how many hidden layers. It's according to the complexity of the data set, for example. So it's the complexity of this decision boundary. What kind of complexity you want to get, right? But remember, because at some point it could memorize your data set. So in fact, if this one is very complex, and it is, if it is just dividing between points like this one, you can say that it's overfitting, right? Because it will memorize the data and it will not be able to generalize. So we need to get something, I mean, yeah, something which can generalize. And therefore we need, it's very important to divide your data set into training and testing. I don't know if I did that here. Maybe I didn't do it also. I used the whole data set for training the model. Maybe this is not correct, right? So I have 400 data points, 200s class 0 and 200s class 1. And the accuracy here, as you can see, it's 100%. So maybe my model is overfitting, right? So you need to repeat this example, but you need to divide the data into training and testing to be sure that, because now there is no guarantees that I'm not overfit. Because you see this decision boundary, it's very complex, which gives me indications that the model just memorize, I mean, the data set, and he cannot generalize in the future, for example. So we cannot check this without dividing the data set into training and testing. So we need to divide it into training and testing sets. We will train the model using the training set, and testing the model performance with brand new data, which is the test set. So in this case, we will be sure that the model will be okay. So maybe you need to repeat this example using training and testing data set. And when I'm not using, in fact, because if you can see here, I didn't use random seed, right? I didn't use random seed here. So when you run it several times, each time you will get different decision boundary. So this is one solution, this is one solution, this is another solution, right? Each time you will get different solution, but you need to have a fixed random seed here if you really want to, if you want to reproduce the results which you got. Okay, so here we used x, y, and x2, right? When we use x, y, and x2, you see that it's a complex data set, right? Because we need to find this complex decision boundary. But is there any way to simplify it? Can we simplify this data set? Similar to the data set which we used before for this circle data set. Is there any way for doing it? Yes, we can, right? So we can use a higher order feature. If we can do it, maybe we can simplify it, right? So do you see here, or interaction, it's not higher order now, but it's interaction. Do you see? This is my data set. When we are plotting it x1 against x2, it will be like this, right? So in this case, the decision boundary, maybe the simple one will be like this one. I need to get someone like this and one like this one. This one will be very good, right? So this is a model which we just solved. So we need to make it like this. But in fact, if you can plot your data set x1 against x1 times x2, the data set will look like this one. In fact, this is +1, this is +1, this is 0, this is 0. Now, +1 will be above the line, all +1 will be above the line, and all zeros will be below the line. So in this case, in fact, we can generate only a straight line decision like this one, right? And in this case, we don't need, in fact, a neural network. We don't need multi-layer perceptron. We just need a perceptron. So in this case, in fact, we can just use a perceptron like logistic regression. We will have two inputs. The first input will be x1. The second input will be the interaction x1 times x2. This one will be connected by omega1, omega2. We have here bias value, and this is y. So the decision boundary will be very simple. It will be omega1, x1, plus omega2, x1, x2, plus b equals 0. If you want to draw the line, we need to assume values for x1, and from this one we need to get x2, right? So if you know x1, we can get x2. If you know x2, we can get x1, right? So we can take, for example, x1 as a common factor. So it will be x1 times omega1 plus omega2 x2 equal minus b, right? So I need to get x2. So in this case, x2 will be minus b divided by x1 minus omega 1 all divided by omega 2, right? So we can find an equation for the line if you want to plot it. We did it here. So so this is the code, in fact. So this is the code. I trained it using a perceptron. Do you see? I just used a perceptron from SK. I used a linear model. We used a linear model. So if you can work a little bit with the features, you can simplify the model. You can build a model which will be more simple, and results will be much better, by the way. So you will get much better. It will be robust, and it will be, when models are less, it's easy to understand it. And, you know, there is something in artificial intelligence, they call it transparent intelligence, or understandable intelligence. So it's artificial intelligence which we can understand it, how the decision making is done. In this system, it's more complex. In fact, for this one, it's more complex, but this one is simple. We just got one line, and all data points above that line, it will belong to one class. All data points below it, it will be another class. But we will use two features here, x1 and x1 times x2. So imagine if you are working with a problem for a bank, for example, maybe x1 it's age, maybe the other one it will be age multiplied by income. So instead of using income, it will be age multiplied by income. Maybe age multiplied by income, it will have more meaning. So so you need to try to check your data set first. Maybe you can turn around it and try to build a model which is more simple. I mean, when the model is very simple like this one, you just imagine this model has only 3 parameters, but this model has 13. I don't know. No, it's had too many. This one is 20. So in fact, this one it's 20 times 2 plus 20 plus 1 times 20 plus 1. So it's 60, 80, 81 parameters, right? So the same problem. So the same problem, we solved it using a model which has 81 trainable parameters, and we solved the same parameter using 3 weights. So you can just imagine how much time it will take for training, how much, I mean, we don't have any risk here for overfitting because it's a linear model, right? So there is no chance for overfitting. So working with those features, and they try to generate new features or higher order features, interactive features. I mean, when we multiply x1 times x2, it means we consider interaction, right? So and this is very good example, in fact, for this one. And here we used a perceptron. So instead of using MLP classifier, we used a perceptron. We used, I mean, we trained it very quickly, and we got very good results. It's very easy to plot. So this equation, right? Yes. For the circle, it's the same also. We solved this example last time. I will go until 1:30 because unfortunately we will have to maybe stop early today for just some meetings and stuff like this. I'm so sorry for this. But for this make circles, we have a data set called make circles. It's a data set provided by sklearn. I mean, in sklearn we have lots of data sets, which is it's provided for people to test systems and test models and stuff like this. So it's a data set which can be customized. So from make circles here, it has some features. You can specify how much noise and how much samples, maybe how many circles. I don't know, maybe this is a default 2 circles, but you need to check it. So you need to search for make circles. In sklearn, you can find all inputs. So we generated those data set. The red one, it's a +1, in fact. So the red, it's a +1. And the blue, it's negative, it's a 0. We have also, it's a binary classification. We have x1 and x2. If you want to build a model, we solved this problem last time using MLP, right? We solved it using MLP because it's hard. We need to find, I mean, it's complex. And so how can we deal with this one? We can try to use higher order features. So we can use, instead of using x1 and x2, we can use x1 squared and x2 squared, right? So in fact, I can use a perceptron, and this perceptron will have two inputs, x1 square. Instead of x1, it will be x1 square. And instead of x2, it will be x2 square. We have here bias. This is output. This is omega 1, and this is omega 2. So the decision line here, in fact, it will be omega 1 x1 square plus omega 2 times x2 square plus b equals 0. This is the equation of a circle, in fact. So now if we can find omega 1, if we can find omega 2, if we can find b, we can draw this circle, right? So we plotted it here. So we can find, yes, I used a logistic regression model, which is linear regression, which is linear model. So we used linear model, we used logistic regression from linear model, and we trained it using, instead of using x1 and x2, I used x1 square and x2 square, right? We used x1 square and x2 square. I trained the model. We can print the coefficient. This one, it will give me the weight values. The intercept, it will give me the bias. So now we have omega 1 and omega 2. Omega 1 equal omega 2 equals this negative value. So finally, we have this equation. Do you see this equation? In fact, it's the equation of a circle which has a radius of 0.91. So this one, it's 0.91 centimeter, for example. Right? So we can draw the circle because now I know the equation. So this is my equation. So I just I assume values for x1 from -1 to +1, for example, and I can just plot the circle. So now the black one here, it's my decision line. You see this my decision boundary? It's this black line. And the black line, in fact, it separates two classes, the yellow one and the brown one, for example. So the one in the middle, all data points which are located inside the circle, it will be +1. All data points which are located outside the circle, it will be 0. Right? So now we can simplify the model, and I can just solve it using logistic regression or a perceptron, because it's inseparable. I mean, if you want to do it, another solution which we did before, so in this case, we will plot it in 3-dimensional space. So we will have x1, x2, and we will have here x1 squared plus x2 squared. So in this case, we will have a plane. We can find a plane. So this one, we'll call it x3 equal x1 squared plus x2 squared. It will be the same, in fact, because it's like omega 1 x1 plus omega 2 x2 plus omega 3 x3. Maybe omega 1 and omega 2, it will be small number or zeros. It should be zeros, in fact. So the neural network or the perceptron, it should try to reduce omega 1 and omega 2, because we need to get this circle, because this circle this is the optimum solution. So now we can solve very complex problem, in fact, using simple model. It's complex data. We can solve it using complex model. I guess we will end with this example. It's a cross validation for MNIST data set. I just implemented here cross validation, and in cross validation, it's stochastic gradient descent classifier. We import it from sklearn, and we use cross validation here for I mean, testing the accuracy. We can go for accuracy until maybe 90%. Maybe it's not very good, in fact, but I mean, in this command, we need to no, this one, it's without cross validation. In fact, it's just using stochastic gradient descent, and the accuracy is 0.9%. It's 90% accuracy, right? But if you will use cross validation, for example, I divided my data sets into 5 classes. So now for each class, we will get an accuracy. For each class, we have this command, which is cross validation score. You need to select a model. Just select any model, right? Select any model, right? We select any model and any classifier, for example, and you need to import this cross validation score. So we will run this model for 5 classes, for example, for k folds, for example, and the scoring will be accuracy. So it will run it for all my k folds, and for each k fold, we will get some accuracy. For k equal 1, we will get this accuracy. For k equal 2, we will get this one. So each one will have some kind of accuracy, and finally, we will get the average accuracy. So the average accuracy will be 91%. So in fact, we use cross validation to check the performance of the model. We didn't train the model. I mean, for each k-fold, in fact, for each k, we start with a brand new model. We initialize it by random values, and we train the model, we check the accuracy. And we will go to the next k-fold, train it for k-1, and test for k equal 2, right? We will repeat this process 5 times. So for each model, we will get some accuracy, and at the end, the average accuracy will be the average of those 5 values. And after that, you can train the model using the whole data set, because now we check the accuracy. I mean, the idea of holdout validation, the idea from holdout validation is to use part from the data for training your model and use the other part for testing the performance of your model. Now we check the already performance, right? We checked the performance. So don't need to keep any data for testing. And in this case, we can just use the whole data for training the model one more time. So here, I'm just yes, no, I didn't. It's in this example, it's MNIST cross validation. So you will see that after cross validation, I used the whole data set for testing the model, because now we don't need to keep anything for testing. We can just use the whole data set for testing my model again. Yeah, so
Question.
Yeah.
If you are using cross-validation in order to train and test your model, how do you then combine the weights and values, the parameters? How do you combine those into one?
Yes, we don't combine. In fact, we don't combine at all. For each k, we start here by brand new model. We train the model, we test the model, right? You know, we selected k equal 5, right?
Yeah, sure. Like this makes sense. So you, at the end here, you have 5 different networks, right?
Yes, correct. You will have 5 different. But each time you start from scratch, you start from random values for weights. We don't increment. So we train one for k equal 1. We train a model and we test it. We initialize a model again and we train and test, train and test, train and test, train and test. So in this case, we will have 5 accuracies. So I can take the average. So the average, it will be 91%, right? So it will be more representative performance for my model. Now if I will have a model with these specifications, we should expect to get accuracy not less than this one, in fact, correct? Because here I trained the model using k-1. Now I'm done with the accuracy because I checked my model. Now I need to build the model which I will use. So next step, will be using the whole data set for training a brand new model. And you don't need to check accuracy again, right? Because the accuracy will be something higher than or equal this one.
And how can you prove that? Can you prove that mathematically?
Yes, no, not mathematically, but you trained this model using k-1. The brand new model, it will be trained using the whole data set, using the whole k values, which equal 5. So I'm just using the whole data for training the model. And then when you increase the amount of data, we should expect that you will get a smarter model, right?
All right.
Because imagine that here we're selecting a k equal 5. So in fact, we train each model by 80% of the data, and the test was 20%, right? Because k equal 5. Correct?
Yeah, sure. That makes sense. I think I understand now. Yeah.
So the final model will be trained using 100%. So should expect accuracy much better than each single model of those cross-validation models. So
but you won't actually have you won't actually have an accuracy of the final model. You know that it's probably better than 91%.
Yes, we assume that it will be better than 91%. At least the accuracy will be 91%. But now we have a model which has been trained with 100%, so it will be greater than or equal this one maybe. Right?
Right.
Yeah. So sorry, we will stop here today, and I'm so sorry for this week, and we will meet again next week. I hope it will not disturb you. So, but you have lots of examples now. You have PowerPoint. I mean, this lecture 5, it's uploaded to Blackboard. You have all code. So please just go to the examples which we used today and last today, and try to, I mean, revisit it one more time and try to make some changes. And next time we will start with I mean, next time it will be very quick. Those feature scaling and the normalization. It's just discussions and stuff like this. And I mean, next time we will try also to talk about mathematics behind the machine learning, because I got some questions from people who want to understand how error backpropagation works. So I'm preparing something for next week to just give you a clear idea about how error backpropagation works. I will explain the mathematics, and also I will implement it, and we will use it for solving a simple example like iris dataset, for example. So sorry for finishing today early, but it's just because I have another meeting, in fact. But also I feel that the amount which you have today, maybe you can just go through it. And if you have any question, please contact me and I will answer you by email. You can just call me by Skype for Business, for example, or by phone. Yeah. Thank you very much.